Welcome to classical mechanics. We are at that point where we have to do Hamiltonian mechanics. So let's just take a quick refresher and look at Newtonian and Lagrangian mechanics. I'm not going to solve the problem that way. I want to solve the problem with Hamiltonian mechanics. So in Newtonian mechanics, the whole idea is that we calculate the net force on an object. And then with that net force, we can use that to solve for the acceleration. And the acceleration is a second derivative of position, so we can get a differential equation of motion. And that's pretty easy, sometimes pretty easy to set up. I'm going to do another video where I show a problem that's actually hard to do in Newtonian mechanics. And I'll do it 3 different ways. I'll solve all 3. But not today. We're just doing Hamiltonian. So that's Newtonian mechanics. Now, the other thing that we did in here was Lagrangian mechanics. So in Lagrangian mechanics, we define the Lagrangian, the kinetic energy minus the potential energy. And the equations of motion are the ones that minimize the action integral. So this is integral of L dt over space-time, and we need to find the path in the space that minimize that. And you get the minimization of that is from the Euler-Lagrange equation. So this says that if there's some variables in this kinetic energy and potential energy, q and q dot, and they can be really anything, okay, any generalized coordinates, then the partial of L with respect to q minus the time derivative of the partial of L with respect to q dot is equal to 0. That gives us the differential equation of motion. So this is really nice because if I can calculate all the forces, then I get an equation of motion pretty much right away. This is really nice because in some cases where I don't know the forces, suppose a block sliding down a plane, I can define my system in terms of motion along that plane, and I don't need to find the contact force, which I don't know and I can't get an equation for. Boom. Okay, so I want to solve this problem. The mass on a spring in one dimension with no friction or anything like that, using the Hamiltonian mechanics. So the Hamiltonian mechanics says a couple of things. Number one, we have to find the Hamiltonian. So the Hamiltonian in general, H, is the sum over I, what is it, P? I don't use Hamiltonian that much. I wrote it down. Pi qi dot. Pi qi dot minus the Lagrangian. So right there you say, well, I got to have the Lagrangian anyway. Why would I do Hamiltonian? We'll get to that at the end. We're going to do it the whole way. Okay. Now, what's P? P is momentum, and you could say mass times velocity, right? But that's not always true. It depends on your coordinate system. So in general, Pi is the partial of the Lagrangian with respect to the coordinate qi. We're going to do all this. Don't worry about that. And then from these two, I'm going to put it over here. I'm going to put all these things over here. So H is, we're in one dimension, so I can just say P q dot minus L. P is the partial of L with respect to Q. And then finally, I get Q dot is the partial of H with respect to P. And P dot is the partial, negative the partial of H with respect to Q. That's Hamilton's equations right there. So that's the Hamiltonian, and that's Hamilton's equations. Let's do it for this mass on a spring in one dimension. Okay. So let's start off and write the Lagrangian. So the Lagrangian is T minus U, and T is 1/2 m x dot squared, and then U is 1/2 k x squared. So if I have the kinetic energy in Cartesian coordinates, I can just write it down. Just a reminder that x dot is the derivative of x with respect to time. X double dot is the second derivative. So right here, L is going to be 1/2 m x dot squared minus 1/2 k x squared. That's the Lagrangian. Now I'm going to use that and this to define the momentum. And you may say, hey, I know the momentum is mass times velocity. Yeah, we all know that, but we should do it anyway, right? Okay, so here I'm going to say P is the partial of L with respect to Q. Q is my generalized coordinate, but the coordinate I'm using here is X. dot. It's x dot, right? Yeah, x dot, sorry. X dot, q dot. So if I do that, here I only have an x dot right here, so I bring down the 2 over 2 m x dot. So P is equal to m x dot, which we knew, so that's fine. So, but now I can write x dot in terms of P. Well, let's go ahead and write the Hamiltonian. H is going to be 1/2 m x dot squared minus 1/2 k x squared. And then I'm going to, it's p q dot. So it's p x dot minus this whole stuff. 1/2 m x dot squared minus plus 1/2 k x squared. Okay, now I need to get rid of the x's. I want to write the Hamiltonian in terms of p and x, right? Because my Hamilton's equations don't have x dots or q dots in there. I have p instead. So I have to get rid of that. So up here, I can say, I'm going to do this a long way. X dot is equal to p over m. So down here, I'm just going to replace my x dots with p over m's. So I get p x dot is going to be p over m. And then I have minus 1/2 m x dot squared is going to be p squared over m squared. And then I have plus 1/2 k x squared. So this is p squared over m minus p squared over 2m, right? Because I have p squared over 2m plus 1/2 k x squared. I know I'm doing a lot of work, but I'm trying to do everything. I'm not skipping any steps, okay? You could do a lot of this just by inspection. So right here, I get p squared over 2m. This whole thing is p squared over 2m, right? Because I have 1 minus 1/2, and then 1/2 kx squared. So I have my Hamiltonian. It's going to be p squared over 2m plus 1/2 kx squared. And I can erase that other stuff because I don't really need it anymore. And you'll notice here that this is the kinetic energy. P squared over 2m is the kinetic energy. And that's the potential energy. So this is kinetic plus potential. So the Hamiltonian in this case is the total energy. Okay? And that's fine. It's not always, but it is here. Now I can use this to apply the Hamilton equations. I'm going to start right here. X dot is a partial of h with respect to p. X dot partial of h with respect to p. So if I take the partial with respect to p, I get p 2p over 2m, or p over m. Now I'm going to do my other one. P dot is negative the partial of h with respect to x. So that's going to be p dot is going to be kx, right? So I bring the 2 down, and I have 2 over 2 kx, negative. So now I have the following equations. I have x dot is p over m. P dot is negative kx. And those are that's my solution, really. We're gonna solve it. Don't worry, we're gonna solve it. That is my solution, because I have a differential equation of motion. That's a differential equation of motion. Now, if you go back to Newton's second law, let's just compare it to Newton's second law. Okay, in Newton's second law, if I did this, which is really easy, I could say negative kx is mx double dot. The force and the mass times acceleration. So x double dot is negative k over m. This is the same thing, okay? But here we have one second order differential equation. Here we have 2 first order differential equations. And that's the big difference here, okay? You can solve this. You could easily show by taking the derivative of this that you get negative. Look, if I take the derivative of this, I get x. Let's do it. X double dot is p dot over m, but p dot is negative kx. And so you get the same thing. Okay. But I'm not going to do that. I want to solve it this way. I just wanted to show you that the solutions agree. Now, one way that we can solve numerically a two first-order differential equations is to do the following. Of course, I'm going to break this into a small time interval. During that time interval, I'm going to assume that P dot is constant, even though it's not. So P dot is negative kx. And I'm going to set that equal to delta P over delta T. P dot is the derivative of P with respect to time, so I can write that as a difference, change in P over change in T. And I know change in T is constant. So this is going to be P2 minus P1 over delta T, where P2 is the momentum at the end of the time interval, P1 is the momentum at the beginning of the time interval. So with that, I can say P2 is P1 plus P dot delta T. So right here, I'm going to solve for P dot and then use that to update P. Step 1, step 2. Okay, but notice that P dot depends on x. So I also need to change x. So right here, I know x dot is P over m, so I can do the same thing. X dot is P over m, which is delta x over delta t. Am I running out of room? Nope, I got plenty of room. Equals x2 minus x1 over delta t. So if I solve this for x2, I get x2 is x1 plus x dot delta t. So I'm gonna calculate the momentum, the derivative of the momentum first, update the momentum, and then I'm going to update x dot. So this is going to be 3, or calculate x dot from that, and then update x. So I have 4 steps. If I did this with a second order differential equation, I only have 3 steps, but it is what it is. Okay, we'll talk about it in a second, but I want to go ahead and do this. So if I want to do this for a bunch of time intervals, I do need to know x1, I do need to know p1. I need to know both of those things. So let's just pick some values up here. I'm going to say x1 equals 1, p1 equals 0, k equals 1, m equals 1. Just because. Okay, it doesn't really matter. And then let's model this system. Now, since we're dealing with p and p dot, x and x dot, I'm going to make what's called a phase space diagram. So a phase space diagram plots momentum on the horizontal vertical axis and position on the horizontal axis. So let's just do this whole thing in Python. Here we go. And then we'll talk about why. I'm in WebV Python. I always do that print 1 so I can save it. Don't need that. Now, let's go ahead. We're going to make a graph. So G1 equals graph, X title equals X, Y title equals Y. Now, it's a phase space diagram. I want it to be like a trajectory. So I'm going to actually make, it square. I normally make my graph skinny. So let's say width equals 400, wrap the line around, height equals 400. Now I'm going to make a curve to graph. I'm called F1, G curve, color equals color dot blue, dot equals true. So if you put dot equals true when it draws, as it's drawing it, it'll put a dot at the leading edge. And so since we're going to possibly trace over ourselves, that's a useful thing to do. So that's why I did that. Now I need my constants. P equals 0, X equals 1, very unrealistic, but who cares? K equals 1, M equals 1, T equals 0, dt equals 0.01. Now let's run this for 10 seconds. So while t is less than 10, you got it because I got a weird thing. And if I ran this in real time, it'd take 10 seconds to run. So let's run it a little bit faster. Let's say rate of 200. So this is do 200 calculations per second. So just like I said before, I'm going to calculate p dot. So p dot is equal to negative k times x. That's what it says right there. And now I'm going to update p. P equals p plus p dot times dt. Now, so remember that in computing this equal signs means makes equal to. So this is the P at the beginning of the time interval, and then I change the value to this. So this is P1 is equal to P2. So just, if you haven't seen that before, I just want to remind you of that. Now I'm going to update or calculate x dot. X dot is equal to P over M. Isn't that right? I forget that's right. And then update x. X equals x plus x dot times dt. Now I'm going to graph it. F1 dot plot xp, and then update time. T equals t plus dt. Okay, let's see if it runs. Yeah, looks good. One of the things I like to do, it's technically a circle, right? Because this is 1 and that's 1, but they're not the same dimensions, so it doesn't really matter anyway. I'm going to, just to make it look cooler, I'm going to set the max and min size for the graph, just so it doesn't have to zoom in and zoom out. It'll just run a lot better that way. And that's just me. You don't have to do that. Okay, and then I'm going to show you one other thing. So up here, let's just say x min equals negative 1.3, x max equals 1.3, y min equals negative 1.3, y max equals 1.3. Now run that again. Let's see what it looks like. See, so then it doesn't zoom, and my thing's a little messed up, but there you go. You know, one of the things I always like to ask people, if the mass is right here, does it go clockwise or counterclockwise in the phase space diagram? So right here, this would be a zero momentum, right? Because momentum is on this axis, but a positive x value. And if it's at rest with a positive x value, then the force is going to pull it back to the origin or back to the equilibrium position. So it'd start moving in the negative direction. So that's negative velocities over here. So it would go this way. So over, let's say up here, I'm at the top up here. What is it doing? Well, up here it's at the equilibrium position. So x is equal to 0. But it's moving in the positive x direction. So it's moving this way. Now the force is pulling it, so it'd slow it down, so it'd go this way. So again, just kind of, imagine what's going on here. But you can see that dot as it moves around. It's kind of cool. Now, if you look at the code, we've done simple harmonic motion numerical calculations before. Oh, I have. And we do have one extra update thing here. Before we would just calculate x double dot, use that to update x dot, use that to update x. Now, but we have the same kind of problem here, right? You have to do things in the right order in order to get it to work well. If I calculate, let's just say I do the following. What if I want to move this up here? If I move this up here, so I'm going to calculate p dot, and then I'm going to use the old p to calculate x dot. You always want to think about the highest order derivative terms first. Momentum is like the derivative of velocity or position. So you want to do the momentum stuff first. Here I'm doing one of the x dot things first. So if I run this, let's just see if I see a difference in the code, in the output. So you notice that it doesn't come back to where it was. And in a sense, when it gets back over here, it's stretched a little bit further. It has more energy. So energy is not conserved in my calculations. Now, I can fix that a whole bunch of different ways. One, I can switch back to the better order, right? I can calculate higher order things first rather than lower order things. I could also do the easiest fix. Always the easiest fix is, well, what if I make the time interval smaller? Well, that kind of works, right? Because now my assumptions are better. So it looks better. It's still not quite. I can see a little bit of a difference, but that kind of fixes it, right? And then you can do other more sophisticated numerical calculations. We're using the very, very basic one of how to update velocity. So that's one thing. Okay, so that's your phase space diagram. That's the solution with Hamiltonian mechanics. Let's just talk about for a second why. What would be the advantage of this? Well, you see the one advantage right there is that I don't have a second order differential equation. I have two first orders. And so maybe that's very useful in some particular cases. And in some systems with many objects, it turns out that that's easier. The other thing is that the Hamiltonian is, if you turn that into an operator, you get things like Schrodinger's equation. Okay, so H psi equals E psi. That's H. But we have momentum and position are operators, and that's why you get them in as derivatives. So that's really the thing that I wanted to mention. There's some other things too. For most cases, you're better off with Lagrange. Most cases in classical mechanics, you're better off with Lagrangian mechanics. You just get that second order differential equation. You have to get Lagrangian anyway. That's the hardest part, is finding the kinetic energy usually. But it is important to include that when we're talking about classical mechanics. I will do some more Hamiltonian calculations. I'll do another problem where I solve it 3 different ways because it's fun, but not today. So that's that. I'll put the link to this phase-space diagram below in case you want it. It's not that complicated, but that's that. I'll talk to you later. The end.